Fine, you can go. So Robert, please.
Okay, thank you very much. Yeah, hello everyone. It will be a busy day. So this is already the second lecture, and we'll have another little activity in the afternoon, which I'll say a little bit about later. Now, I'm slightly behind schedule. Today we'll at least start to discuss medium mass nuclei. But we have to finish off the no-core shell model discussion that we started yesterday. And there are a few important things left. I'll start with a little reminder what we discussed yesterday. And essentially we stopped with a discussion of the specific type of model space truncation that is used in the no-core shell model. This model space truncation is in the spirit of CI lectures, CI methods. That means you convert the Schrödinger equation into a large-scale eigenvalue problem, and you have to define some kind of truncation for your Hamilton matrix so that you can handle it numerically. And the no-core shell model is defined by two kind of key elements. First of all, you use a spherical harmonic oscillator basis as a single particle basis from which you build Slater determinants, and you truncate this infinite set of Slater determinants with respect to the harmonic oscillator excitation quantum number, which we call Nmax. This gives you a finite matrix, and actually this is in the specific form of the relative coordinate or Jacobi coordinate version of the no-core shell model, exactly what we discussed earlier in connection to the similarity renormalization group. There I showed you such a huge matrix representation. Now the specific case of a relative coordinate harmonic oscillator basis. And we discussed the effect of the SRG transformation itself. But actually what we did then was a no-core shell model calculation by using this matrix or little submatrices, which I cut out according to the total energy quantum number, this E, in my three-particle harmonic oscillator basis, and I solved the eigenvalue problem of this matrix. And that was shown in this first convergence plot, which we discussed, where as function of Nmax, now this Nmax is the Nmax, this number of oscillator quanta in the no-core shell model truncation. And for this specific case, the Nmax is just the largest value of this principal oscillator quantum number, this E, that I consider. So Nmax means I cut out blocks of different size in this energy quantum number. I increase the size of these blocks, solve the eigenvalue problem for each of the blocks, and observe how the ground state energy, the lowest energy eigenvalue of my eigenvalue solution, behaves as function of this matrix size or the Nmax parameter. And we saw that for the typical chiral 2+3 nucleon interaction, I get this kind of behavior, which tells me, okay, I have to go to pretty large Nmax, maybe something like 20, to get a stable ground state energy which doesn't change anymore if I go still bigger with my basis. And this is what I call convergence. So I get a converged answer in something like Nmax 20. And now the big deal was that we can use this unitary transformations, the similarity renormalization group, which introduces this flow parameter alpha, to pre-diagonalize this matrix, so to eliminate off-diagonal matrix elements here. And that quite intuitively tells you that you have an easier job if you cut out a little matrix here, because all the stuff up here is zero in any case. It will not couple to these high-lying matrix elements, so you will have much faster convergence. And this is what you see if you do the actual calculations. Now you could start to talk about a converged result maybe around Nmax 10. There's still a little bit of movement, but this is due to the specific structure of this three-body system, which we discuss here. And based on the quantum numbers that I specified up here, this is the triton, so hydrogen 3. which is a very loosely bound system, very extended wave functions. And we had that discussion also in connection to the deuteron already. For these extended wave functions, you need large basis sets to build up the long-range structure. This is nothing I have addressed or cured or simplified with the SRG. There I really need the basis, and that's the reason for this kind of slowish convergence out here. But in the region Nmax 10, you're good to go. Last time somebody asked a very clever question, namely, okay, can I go all the way throughout the nuclear chart with this no-Cauchy model? And if we keep in mind that we want to reach something like Nmax 10 to get a converged answer within soft SRG evolved interaction, we can just look what this means for different nuclei. And this is shown in this plot here, where I have the Nmax, so my basis truncation parameter, and I really plot the basis dimension as function of this Nmax. Now, this is really the number of rows and number of columns in your huge matrix. And it's a log plot, and it goes up to 10 to the 10. So these are large matrices, 10 to the 10 rows times 10 to the 10 columns. And this is kind of the limit what we can actually do computationally nowadays. So we can solve the eigenvalue problem in a very specific sense for something like an up to 10 to the 10 by 10 to the 10 matrix. It's not always possible. It depends on the properties of this matrix, and we'll come to that in a minute. But this red region up here is kind of the danger zone. So there it starts to become so expensive in computing terms. And when I talk expensive, I really mean the largest computers that exist, that you cannot handle the problem anymore. So this is not feasible to go up here in this red regime, really. If I, on the other hand, expect that for convergence, I need something like Nmax 10, then all these smaller Nmaxes are not really helpful to get a final answer to the problem. So therefore, in this regime, I don't expect converged results, and I'm not done with the calculation in some sense. And now all these lines in this plot, they indicate how the basis dimension, the matrix size, really behaves as function of Nmax. For light nuclei like helium-4, this is the black line here, that's still okay. If you go to something like boron-10, so that's a typical mid-p shell nuclei, then you have this blue line here, which is okay, much steeper, and you see that you are already touching this danger zone, the red zone up here, and you just about make it into this white area where you can still do a meaningful calculation Nmax 10. So this is about where it's getting hard. And the extreme case is carbon-12, where you just have this little chance, or the last hope up here is the Nmax 10, which would be very, very tough to do. Has been done, so it is possible, but it's very costly in computational terms. But this tells you, if you want to go to sufficiently large Nmax, your reach in particle number, in mass of the nucleus, is very limited. And if you use this pure NCSM, you run out of steam typically around mass 12. So this carbon-12 is the last nucleus that is typically done in the standard no-Cauchy model. So now there's one more comment asking for materials for the lectures. I'll say something to that later. And then a question, is this calculation done in relative coordinates or with a second quantization framework? Now we have to go to the second quantization, so the single particles later determinant type picture. Because the relative coordinate calculations, they stop to be meaningfully possible at mass maybe 5 or 6 if you really push it. Because there's a lot of extra work going into the construction of these Jacobi relative coordinates 6-particle matrix elements. I briefly showed you how the 3-particle basis sets look like. You might remember this long list of angular momentum quantum numbers. And if you extrapolate from there to a 6-particle basis, which would be the thing to use in a Jacobi NCSM formulation, this gets out of hand with respect to all these angular momentum couplings. So you simply cannot handle that anymore. And therefore, typically we do something like up to mass 4, helium-4, in these relative Jacobi coordinates. And from there on, we have to switch to Slater determinants and second quantization for the heavier systems. And also this basis dimension here, this is for the Slater determinant version of things. That's encoded in this tag M scheme here, which is slang. But this, what I say here, is only true for the Slater determinant framework, and this is the only way to go beyond these very light nuclei at all. Okay, now this is maybe not good news, so we have to find ways to maybe push a little bit, or we have to go to different methods, and this is the main topic of today's lecture. But before going there, maybe we ask ourselves, 10 to the 10 by 10 to the 10 matrix, this sounds crazy. How can you possibly even think about solving an eigenvalue problem for such a large matrix? There's no chance to store such a matrix ever on any computer on Earth in main memory. So this is something where you might ask, how can that be? And therefore, I want to go a little bit into the computational aspects very briefly, very low, very high level, but just to give you a flavor why this is possible at all. Francesco just asked, does NCSM work well for odd nuclei? Yes, so at the moment there is no restriction whatsoever on which type of nucleus you put in there. Whether it's even or odd, closed shell, open shell, fully open shell, semi-magic, doesn't matter, because we treat them in a very, very kind of naive or brute force approach with this basis expansion. You don't assume anything about specific quantum numbers, closed shell characters, gaps, or so. It doesn't matter. You just do this large scale basis expansion, and you always have to check for convergence. And there are nuclei where convergence might be better and others might be worse. That might depend on the specific structure of the individual nucleus, but in principle, it's applicable to any kind of nucleus and also to the excited states automatically. We mainly talk ground states, but later I'll also show results for excitation spectra. Okay, now how is this at all possible? And this is not always possible to deal with such a big matrix. You need special properties of this matrix. And these properties are essentially twofold. Number one, you don't really want to know the full eigenvalue spectrum of the matrix. You're not interested in an eigenvalue at 1 GeV excitation energy, which might exist in your matrix, but it's not meaningful at all, neither from the physics point of view, nor from the things that the method is able to describe. Typically, you want to know a few low-lying eigenstates, the ground state and a few low-lying excited states. That's it. In comparison to the 10 to the 10 eigenstates that this matrix has formally, theoretically, not of interest, just a few low-lying ones. The second thing, which is important, these matrices are very sparse. That means the majority of the matrix elements is 0 to start with. If you look into a typical case for a typical model space size and an average nucleus, you find something less than 0.01% of the matrix elements are actually non-zero. So this picture is a little bit misleading because I threw out lots of zero matrix elements here to make this plot nice. There's much more white in this plot usually. And these two things, only a few low-lying states plus very sparse matrix, that enables you to use a very powerful class of algorithms, namely Langshas types algorithm, or sometimes they are called Krylov space algorithms, which solve the eigenvalue problem in an iterative fashion. So you don't do this full diagonalization of your matrix by transforming, adding, subtracting rows and stuff, but it is a much more elegant approach. And in particular, this Langshas algorithm is magic. And I will explain this algorithm in a minute. And the thing that really limits you in this calculation is not really the basis dimension, so this 10 to the 10, but it's a number of non-zero matrix elements in this matrix, because you have to typically store them. You could think about computing them on the fly, but that would make your calculation much slower. Typically they are stored, and typically they are stored in fast memory, so in RAM. You can distribute them over many, many nodes if you have a big computer, no problem. But this is typically the limiting factor. How many terabytes do you need to store all the non-zero matrix elements? And as I said, it would be impossible to store any of these matrices if it wasn't for such a very sparse structure. And in typical calculations, we use something like 1, 2, 3 terabytes for these matrices. So this is getting big. There is another question. May you elaborate on low-lying states versus small n max? Now this is a disadvantage of chat, because otherwise I would ask immediately, what do you mean by that? I mean, low-lying states, this is referring to the spectrum of the Hamiltonian, the physical states that I want to compute, the ground state, the first excited 2+, some other states in the spectrum of the nucleus. This is what I mean by low-lying states. Small n max is just a statement about the size of the basis I use, so a purely technical computational thing for expanding my eigenvalue problem. So n max always just refers to basis stuff. Low-lying states is the physical eigenstates that I'm interested in. Maybe that is your question. If not, then please try again. Okay. So this Langshas algorithm, which makes that all possible, is actually super simple. Although it's magic, but it's simple. This is it. That's all. And I wrote it here in kind of pseudocode, if you like. The thing is, what eventually happens is you start from your huge matrix, 10 to the 10 by 10 to the 10. And what this little algorithm does, it converts this matrix into a small tridiagonal matrix. So you only have matrix elements on the diagonal and the neighbors here. The rest is 0. And this matrix has an index m, which is essentially a counter for this iterative process. So you can make this matrix larger and larger if you like by doing more and more iterations. The math behind that, and that's this whole Krylov space business, is in the end, the eigenvalues of this small matrix throughout the iterations will converge to the eigenvalues of the big matrix. And this convergence starts from the most extreme eigenvalues, the highest ones and the lowest ones. We are only interested in the lowest ones, so that's good for us. We ignore the highest ones. But that means if I just want to have 5 or 10 of these low-lying states, so the lowest eigenvalues of my Schrödinger equation, then I might not need to go too far in my iterations here. And in practice, I only have to go to something like 30 or 40 iterations, which means a 30 by 30 matrix, which you can easily solve with any eigenvalue solver on your phone or whatever. So this is what is done here. You convert a big matrix into a small matrix, which has the same extreme eigenvalues once they are converged. Now the question is, okay, that sounds nice, but is it really computationally feasible to do this thing in between? And in order to understand that, we have a quick look at what happens there. So there are a few vectors that I need. Actually, I need 3 vectors, and these are the V0, V1, and then the indexed ones, Vi, and so on. These are vectors that have the same dimension as your matrix. And these vectors are being used to compute a matrix vector product. This is the only place in the whole game where your big Hamilton matrix ever enters. And it only enters through a single evaluation of a Hamilton matrix times vector product. So from the computational point of view, what you have to be able to do efficiently is a simple matrix vector product for a sparse matrix. And there are many clever ways to do that. Nothing else. You don't manipulate the matrix. That's important because you could never do that for such a big thing. You just have to evaluate this. And then you just do simple operations on these vectors. You have a result vector here. You compute the scalar product. You compute a norm for this vector. So these are all super simple and super efficient vector operations, which can be very efficiently be implemented on any computer. So the thing is, this is extremely simple what happens there. And it's just this for loop which runs over the number of iterations that you would like. And this M, as I said, determines how big your resulting T matrix will be. And because of this, we are able to do these calculations. We store the Hamilton matrix elements once distributed over many, many nodes. And then we only have to do 20 or 30 times for each iteration. You need one, this matrix vector product, and that's it. Okay, question from quantum chemistry. Very good. Davidson algorithms are frequently used in CI. Is this also useful in nuclear physics, or is it not as successful? We looked into that a long time ago, but it doesn't help. So it's much easier to go with this very simplistic Langshas algorithm to large, scalable, parallel implementations. It's really a question of computational, I don't know, not efficiency, but ease. How can you parallelize and distribute such an algorithm efficiently? And because it's so trivial here, that's a piece of cake really to do all kinds of parallelizations here. So these Davidson algorithms, they have been looked at, but they're not used in nuclear applications. Okay, now we can have a look at what really comes out of this. And this is just for an illustration. If I crank up this number of iterations I do to construct this T matrix, that's here on the x-axis, and I just plot all the eigenvalues of this T matrix, the small matrix. And after one iteration, so the very left here, there is just one eigenvalue because it's just a number. There is not even a matrix. Then in the second iteration, you have two eigenvalues, third iteration, 3. So you see the number of eigenvalues goes up, one in each iteration because the matrix grows. But you see what happens with these eigenvalues. So the lowest one really converges super fast and stays put for all of the future. This is the ground state. And by the math behind it, it's guaranteed that this is the same eigenvalue that the big matrix would have. You see the next state that comes in a little slower, but after 10 iterations, again, this is flat. Third state comes in still slower, but 15 iterations flat. So you can guess if you do something like 20 or 30 iterations, you have the lowest 10 eigenstates converged. You're done for the low-lying states in your spectrum. So you really don't need many of them. If you look closely, there are some stray points here. This guy, for example, this doesn't fit in here. This is a tricky numerical issue with the Langshas algorithm in this super simple form. Because of numerical inaccuracy, finite floating point precision of your computer, you can lose orthogonality of different eigenvectors. And then they collapse to the next lower one, and this is on the way to become a second ground state. So this is a little annoyance in this algorithm. You can either accept it or improve the algorithm with an explicit reorthogonalization. All this can be done. But this is really just the vanilla plain simplest version, and it already works, which is really, for me, always a miracle. Now, this all doesn't help us with this N-max wall, so the dimensionality of the matrix. You cannot go much beyond this 10 to the 10. So we need other ideas to somehow simplify the problem to get further in mass number. Otherwise, we are stuck at mass 12 with this full no-Koshal model. And I'll present two ideas which will help. One of them is the so-called importance truncation. And I just present it because the idea is really intuitive, and it hints at kind of benefits you gain from combining different many-body methods. And this is a paradigm that we'll build on later. So we'll do much more of this hybrid constructions. And in a sense, this importance truncation is the first one. So as a bottom line from the discussion that we had so far, the statement converged NCSM calculations are limited to the lower until mid-p shell, so this carbon-12. If we try the next interesting nucleus, oxygen 16, then you cannot do, and nobody can do, the Nmax 10 calculation anymore. And if you do up to Nmax 8, which I show here, then it's pretty obvious that these calculations are not converged. So the ground state energy still changes with Nmax, and you cannot really read off or predict what the converged value will be. Even if you try extrapolations, which we are doing, this is more or less a linear trend. So it's very, very hard to extrapolate some finite result out of that. It would be so useful to go just one or two steps further to this Nmax 10 or Nmax 12 to get a better converged result and have a chance with extrapolations. So we don't need much. And the question is, how can we squeeze out this extra 2 steps in Nmax? And the idea here is, in order to really reduce the dimension of your matrix, you look at all of the basis states that you have in your Nmax 10 or Nmax 12 space. You don't keep them all. You kick out some states, you select states, and you only keep those states which are important for the description, for example, of the ground state of oxygen 16 with this specific Hamiltonian. Now, the million-dollar question is, how do you decide or detect which states will be important in the final solution, so in the final expansion of your eigenvector? Of course, if you have this expansion, you see states which have tiny, tiny coefficients or even 0 coefficients. But in order to see that, you have to solve the problem. You've gained nothing. You have to be able to predict that without doing the calculation. And you can predict that with a very simple many-body method, namely many-body perturbation theory. You just use perturbation theory to estimate the coefficient of a specific basis state in the expansion of your ground state, let's say. And if that coefficient is larger than a threshold value, you keep that state. If not, you throw it out. And only with this residual states, you do the eigenvalue problem, which is then much smaller. And formally, this is not complicated at all. So what you typically do, you start from an initial approximation for your target state, which is, for example, the ground state. And that is, again, an expansion of this target state or reference state in a harmonic oscillator Slater determinant basis. And you have coefficients which you got from some prior calculation. For example, in the last Nmax that you could do easily with a full NCSM, for example, the Nmax 8 for oxygen 16 that I showed just a minute ago. So that could be your reference state. That's already a pretty substantial, highly correlated state. It's just not fully converged yet. And then you use that and combine it with simple perturbation theory. You all know that from your quantum classes. The coefficient for a first order correction to the states in perturbation theory is simply given by the matrix element of the unperturbed state, which is the reference state in our language, the state which you are probing, where you want to decide whether to keep that or not, and the Hamiltonian, and the whole thing divided by an energy denominator. And this structure, which is just the first order perturbation theory coefficient correction, defines kappa, and kappa is what we call an importance measure. That determines how important this basis state is, and you simply apply a threshold to this measure. You only keep coefficients which are larger than a kappa min smallest measure that you would like to consider. And this defines your importance truncated space, and you solve the eigenvalue problem for this space. Now you have this extra truncation parameter, kappa min. Before we had n max. The n max is still there, but now I have kappa min in addition. So I have to be careful with these two parameters. And what we do typically, we want to get rid of the kappa min by looking at the dependence of our eigenvalues on kappa min and by doing an extrapolation in this kappa min. And this is for Oxygen 16. Just again, the Nmax 8 example, because there I have the exact value in the full NCSM, that is this red line here. The blue symbols are results from different NCSM calculations with different importance threshold. So the kappa min is down here. And you see that this is a very smooth dependence on this kappa min. And if you look at the scale here, you see that the change is tiny. So we are hunting for precision here, really. So even with this last value, I would have a pretty good approximation to my exact result down here, but I don't need to stop there. I can simply do this simple polynomial extrapolation, and I hit my exact result with a very, very nice accuracy. So in this way, I can beat this Nmax boundary by additionally selecting states and using this simple extrapolation. You cannot really appreciate how much simpler these blue dot calculations are in comparison to this red line calculation, because I didn't show you the dimensions. But the thing is, the basis dimension of this calculation here compared to this red line full NCSM calculation, they differ by 2 orders of magnitude. So you've saved quite a bit in matrix dimension, and you don't pay much in energy and you don't pay much in accuracy. And that allows you to go further. We can do Nmax 12 now without problems. Here I don't have a red line because nobody can do that full space, but you see, you do have to account for a little bit of uncertainty. That is this gray band here due to the extrapolation that we do, but that's it. And this opens up a whole extra range of nuclei which we can treat. And essentially that shifts the limit from mass 12, the carbon 12, to something like mass 25, as I will show you in a minute. There's a second thing that you can do, and that is playing with your single particle basis. So far we kept to our harmonic oscillator. That's pure harmonic oscillator, no Cauchy-Riemann. I can sacrifice this harmonic oscillator choice. I will pay something, for example, this translational invariance problem will pop up, but maybe I gain something in terms of convergence. And therefore you can look into the performance of different basis choices in this NCSM context. We discussed the harmonic oscillator so far. We need it in any case to compute the matrix elements. That's the first step. But after that, I could transform to a different single particle basis. What I will lose is this nice property of the separation of center of mass in intrinsic states. But one physics point I might gain is something we also discussed, namely that the harmonic oscillator has the wrong asymptotic behavior. You have this Gaussian fall off at long distances. But for a typical bound state in a potential well, you would expect an exponential fall off. So this wrong asymptotics is the reason for some of the slow convergence that we see in some observables. And you might correct for that by choosing a different basis. Now, what other bases come to mind? One thing that is a pretty obvious idea is to go to a Hartree-Fock single particle basis. You can use the Hamiltonians that we discussed to do a simple Hartree-Fock calculation. The ground state energy you get out of Hartree-Fock will be pretty bad. Typically, you get, even after SRG evolution, something like half of the real binding energy. But still, you could use this single particle basis that is generated through the Hartree-Fock iteration procedures, and Gianluca discussed that with you. You can use that as a basis. Why not? You transform all your matrix elements into this basis, and you do the NCSM calculation with this Hartree-Fock single particle states. There are still other alternatives, and one which turns out to be extremely useful is what we call the natural orbital basis. So there you do little more than Hartree-Fock. Hartree-Fock lacks all of the correlation information, and therefore you do not get a good approximation of the ground state energy. Maybe one could use perturbation theory again to improve things here. And you can by doing perturbation theory on the density matrix. So Hartree-Fock also gives you a density matrix, which has a very simple structure. And you can correct this density matrix for correlation effects through perturbation theory. And then you use the eigenstates of this density matrix as basis. And the eigenstates of the one-body density matrix are called natural orbitals, and therefore this name. I don't want to bore you with the details here, but just the idea is once you go here, you have additional information encapsulated in your single particle basis, which is not yet well represented in the Hartree-Fock basis. And this is something which is important for the usefulness of these bases in NCSM type calculations. Now let's look at this. As a pet example, I now use this oxygen 16 calculation. And what I show here is pure harmonic oscillator, so standard no-core shell model. And it's a very typical diagnostic plot, if you like. What's shown here is the ground state energy of oxygen 16 from NCSM calculations with different Nmax parameters, starting 2, 4, 6, 8, 10. And I repeat this calculation for different harmonic oscillator frequencies. So the harmonic oscillator always comes with a free parameter, this frequency, which also at the same time determines the spatial size of your oscillator wave functions. This parameter is free to choose. I mean, you can choose the stiffness of your oscillator if you like, and this will affect the convergence of your results. And therefore, if you do this classical no-core shell model with a harmonic oscillator basis, you always go through these plots. You look at different oscillator frequencies and you compare the convergence behavior if you increase Nmax for these different frequencies. And the picture here is very characteristic for ground state energies. You always have this kind of parabolic behavior with a minimum. And at this minimum, or in the region of the minimum, you see that the convergence, so the succession of these points, looks nicest. So you get best convergence, fastest convergence. If you work with an unfortunate frequency out here, you come from all the way up here and then dive down and you're still not at the same level like the other frequencies. So you always have to watch this frequency dependence of your convergence pattern, and you typically pick, after doing the calculation, the best frequency in terms of convergence rate to extract your final result. That's tedious because you have to do many calculations here. It's always a full-fledged Nmax 10 calculation, which you have to run again. So that's expensive. But this is what's always hidden behind a harmonic oscillator NCSM calculation. Now, how does it look like for the other basis sets? Let's first look at Hartree-Fock. This is the same kind of plot with a Hartree-Fock single particle basis, and it looks very different. You don't have these parabolic curves anymore. It's more or less straight lines. They're slanted a bit, but not much. And you see that the convergence pattern, so the behavior of successive Nmax points here, it really looks bad. It's almost same distance between these points. So you don't have this kind of nice, rapid, typically exponential convergence like here. Even for the same basis size, Nmax 10, so same cost for the calculation, you are still higher up in energy than in the oscillator basis. So Hartree-Fock doesn't work at all. Very bad idea to use Hartree-Fock. And it took us a long time to understand why. Therefore, we came up with these natural orbitals, and they combine the best of the two worlds. First of all, you have this horizontal lines for the different Nmaxes, but at the same time, you have a convergence pattern which is as good or better than for the optimal frequency in the harmonic oscillator. And this is extremely useful. So you're as good or better as a harmonic oscillator, but essentially for each and every value of the underlying oscillator frequency. So you simply don't have to care about this frequency parameter anymore. You pick your standard value, which might be h bar omega 20, and simply do this one calculation, this one sequence of Nmax, and you're done. You're guaranteed to have the best possible convergence. And that's extremely, cost effective. It saves a lot of computing time because you can forget about this frequency optimization. This gets even more relevant if you go to other observables. And so far we only discussed energies, but the target is really many, many other observables which we want to compute. For example, radii. So RMS radius of a nucleus. And this is the same kind of plot now for the point proton RMS radius of a nucleus. That's kind of related to the charge radius that you measure in an experiment. So we want to be able to compute that. And now it looks really weird in the harmonic oscillator basis, but this is again a very typical picture. What you see is that as function of this basis size Nmax, if you start from large oscillator frequencies, which means very small extent, spatial extent of the oscillator wave functions, you have this convergence from below. These points creep up with Nmax, and they creep up slowly. If you start for very small oscillator frequencies, that means large spatial extent of your oscillator wave functions, you approach this radius from above. And that's quite intuitive. Your wave functions that you have in your basis are simply too large for your nucleus of choice. So you use a superposition of many of these wave functions to represent the smaller extent of the density distribution of the nucleus. That's the situation here. Here it's the opposite. You start with a way too small basis and you have to build up size in order to represent your density. And there's one sweet spot again, and it's typically at a different place in h bar omega as compared to the energy. And this sweet spot is where all these lines cross and you essentially have a stable constant result irrespective of h bar omega. But the problem is to arrive at that, you have to do all these h bar omega calculations again to determine where the sweet spot is. And again now, the natural orbitals, and in this case also Hartree-Fock, help a lot because now you've built in the natural size of the nucleus, so to say, right into your basis to start with. And therefore, first of all, it doesn't depend on h bar omega anymore, and you have this very smooth and rapid convergence here. Nmax 8 and Nmax 10 now on top of each other, you're done. You have this very smooth convergence, and of course you agree with the result that you would have predicted from the oscillator calculation in a much more costly fashion. So this is one other trick that we can use, and combined this importance truncation plus natural orbital basis choice, that can now be used to compute all kinds of observables. Here I just have a collection for carbon-12. That's the ground state energy. That's the excitation energy for the first 2+ state, the first 1+ state. Here's a quadrupole moment for the 2+ state, the E2 transition strength from the 2+ state to the ground state, and here an M1 transition strength from the 1+ excited state to the 0+ ground state. All of this spectroscopic information you get out of this calculation. Yeah, it's not a separate calculation to address an excited state or to address an electromagnetic observable. It's all just the eigenvectors that you got from your diagonalization, which give you this information. And all of these converge nicely, as you see in the natural orbital basis, which is used here. And because of this nice convergence plus importance truncation, we can push the range of applicability to something like mass 25. So here I actually show calculations for all of the oxygen isotopes from oxygen 14 to oxygen 26, which is hidden in here and not labeled. And I show you this Nmax trend of the ground state energy up to Nmax 10. and you see that they are all very nice converged, or that you can do some meaningful extrapolation because you're sufficiently close to convergence. So we can do a much larger set of nuclei now with these additional tricks, if you like. And we can compare to experiment. This is now a different representation. Here's mass number for these oxygen isotopes, ground state energy again. The bars are the experimental ground state energies for even and odd isotopes. And the points, the blue points, are the results of these NCSM calculations with a natural orbital basis. There are two types of points. The light blue points, they really use the full Hamiltonian with the explicit all the terms that come from the three-body force. And the dark blue symbols, they use something that we call normal ordered two-body approximation. And what this is, I will discuss in a minute in connection to the medium mass methods. This is the end of the NCSM discussion. I just want to mention that the NCSM is a big family. So we've discussed the harmonic oscillator, NCSM in relative coordinates, importance truncation, natural orbitals. And there are many other flavors of NCSM style calculations. There's a big effort in symmetry adapted NCSM calculations where you take additional symmetries in addition to rotational symmetry into account. You can try to include continuum, that defines the so-called gamma of NCSM, or more refined versions of continuum inclusion using resonating group methods, so that bridges really towards reaction theory. And that has been very actively developed in the past couple of years in this NCSM context. Okay, maybe I take a breath and ask for questions from your side. Anything left on this NCSM discussion?
Hello, can you hear me now? Yes. Okay, sorry, I wasn't able to use the microphone earlier.
Yeah.
So if anyone else has to ask anything, or just when I asked about the low line state and max, probably I just got confused from what you from what I remembered from yesterday, because there was that discussion about so how to truncate the basis. We can either choose a maximum state and consider all the configurations between them, or consider a maximum number of excitation quanta.
Okay. Yes. Okay. Yeah, I understand that point. Yes, that's tricky. I mean, the truncation of the basis with respect to the highest state, that was a statement concerning the single particle basis that you put in. And when I talk low-lying states, then I'm thinking of many-body states. So
okay.
So that's kind of, I'm really thinking about the solution for my A-body problem, where I pick out the lowest few eigenvalues. And the discussion with the full CI type methods, where you truncate the single particle basis to lowest states, but that's really at the single particle level. So that's the difference there.
Okay. Now I see now. Okay, of course. Thank you.
Okay, great. So is there anything else? Okay, if not, then we ask ourselves, can we do better than that? And better means, can we expand the reach of these ab initio methods still further? So we are at mass 25, 26, that's pretty good, but can we go further? And we cannot go with a straight NCSM, but we can look at other ideas and kind of other formulations of methods that behave differently with respect to their scaling in mass number. So just remember for now, the NCSM was this large eigenvalue problem with an max truncation, and essentially I get explicitly the information on the eigenvalues and eigenvectors, and that works up to mass around 25. If you think back to the first time you saw an eigenvalue problem, instead of looking at it like this as a matrix eigenvalue relation, you could also think of it like this. what the solution of the eigenvalue problem does for you is you convert this matrix into a diagonal matrix, which has all the eigenvalues on the diagonal. And the transformation from here to there is given by the eigenvectors. Therefore, in slang, we often don't talk about solving an eigenvalue problem. We simply say we diagonalize the matrix. It's equivalent. It's the same thing. And by solving the eigenvalue problem in the NCSM style that we did before, we essentially construct this diagonal matrix explicitly. Now remember what we had in terms of language and ideas when discussing the similarity RG. I used terms like decoupling. I said I want to suppress off-diagonal terms in my matrix, and this is decoupling. And if you use this language of decoupling instead of diagonalization, then the transition from here to here is kind of the most extreme case of decoupling. You have decoupled everything from everything. No single state in this basis representation here, which are the eigenvectors, talks to any other state anymore because all the off diagonals are zero. So maybe we can go a little further with this decoupling paradigm, with this decoupling idea. And actually, this is the language and the basic conceptual change that you use in some of the most successful medium mass methods. In principle, you forget about the solution of this eigenvalue problem. You ask yourself, can I formulate some kind of transformation U, which goes from here to here without solving the full eigenvalue problem? And if I'm honest, I don't even have to go here. I'm not interested in these high-lying eigenstates and eigenvalues. We even didn't compute them in the NCSM. Would be fine if I do something like this. I go from this matrix to a matrix like this, where the only thing that happens concerns this upper left corner. For the low-lying part of the spectrum, I have decoupled the states here from the rest. That means these lines, columns and rows in this that connect to this upper left corner of my matrix, they are suppressed. So this is kind of a partial decoupling. I'm only interested in the stuff down here. Nobody cares about the states at 1 GeV because they're meaningless in any case. And now the question is, can one invent methods which do something like this partial decoupling of the low energy states from all the rest in my basis representation? And actually, there are two methods which do exactly this. They seem to be very different, but they are related to each other. And these two methods are the in medium similarity renormalization group. So I recycle this SRG idea in a slightly different implementation. And the different implementation is this in medium thingy here. And the second method is coupled cluster theory, which does the same in a slightly different way. And these are the two methods I want to discuss now. And these methods need a little bit of an extra piece of formal underpinning and language. And this is the normal ordering of operators that was mentioned a couple of times already. And I want to briefly discuss the math or the basic many-body quantum mechanics behind that before I discuss these two methods with you. So you might have heard all of this in some advanced quantum lecture. It goes back to our second quantization discussion in the beginning. So you remember we discussed these creation and annihilation operators, and my original notation had this full single particle label alpha I as a lower index. I'm getting rid of that now and simply call the annihilation operators AI and the creation operators AI dagger. So I leave out the alpha. And already after we introduced these creation and annihilation operators, we discussed this particle hole type picture. So you now start to build your many-body Slater determinant basis from a reference Slater determinant, which just has a specific set of single particle states occupied. And you can write that as a chain of creation operators applied to the vacuum state, which doesn't have any particle content. And with this as kind of the starting point, you can apply annihilation and creation operators to construct all kinds of other later determinate states of your many-body basis. You can essentially change the single particle state of one particle out of your Slater determinant by applying an annihilation operator and a creation operator with different indices. You can do that for 2, 3, 4, 5, 6, 7, A. And this is a hierarchy of particle Hall excitations in your basis of Slater determinants. Okay, that we had before. I have this kind of compact notation now for this 1 particle 1 hole, 2 particle 2 hole excitations, which has the symbol for the reference state and then just the indices that you eliminate, that you remove in the bottom, and the indices that you create new at the top. And I have a second convention, that's a famous index convention, because now you have a subset of states which is kind of special because it already appears in your reference state. So these first A states, alpha 1 to alpha A, they are somehow different because they are already present in the reference state and they get a specific index. So whenever one of these indices here refers to a state which is already occupied in your reference determinant, then this state gets indices A, B, or C, and it gets the name Hall states, which I find terribly confusing, but which is standard slang or standard terminology in our field. It just indicates there is a particle in the reference state, and if you want to do something interesting, you have to create a hole instead of this particle. You have to remove this particle. So therefore, these A, B, C indices, they appear with the destruction or the annihilation operators here. You remove these particles and create a hole, therefore Hall states. All the other states which are not occupied in the reference determinant, they are PQR and they are called particle states. So these are the unoccupied states, and you can put a particle in there via one of these particle Hall excitations. So these are the states that are coming with the creation operators here. And if I want to sum over all states, I use IJK. No? You don't have to memorize that because it's kind of always obvious what you're talking about in terms of particle Hall states from the context, but it will be used, therefore I discussed it. Now with this, you can start to understand and define what this term normal ordering of operators means. So it's a statement about the ordering of a chain of creation and annihilation operators that are connected by an operator product. And in very superficial terms, you have these creation and annihilation operators, and you define normal order to be that the creation operators are on the left, all of them, and the annihilation operators are on the right, all of them. So these little particle Hall type structures that we've used before, they are in normal order because all the creation operators are on the left and all the annihilation operators on the right. They're in normal order with respect to the vacuum state. And this is how we use them. For example, when we discussed the representation of kinetic energy or potential in second quantization, this also appeared in this particular order with respect to vacuum state. Now, in a calculation, it can happen that this order is mixed up. For example, if you start evaluating these commutator terms that we've already seen in the SRG discussion, then you suddenly have creation operators on the right in your long chain of operators. So therefore, you define something that's called the normal ordered product. It's just a symbol, a formal object, if you like, and it's this curly brackets. If you have any string of creation and annihilation operators in curly brackets, then this tells you before you go on, you have to sort these operators, bring them into normal order, put the creation operators to the left, and then annihilation operators to the right. And in order to do that, you have to do transpositions, change orderings, commute operators. And that might give you minus signs because you have anti-commutation relations. So whenever you see a syntax like this implies you have to do this sorting and you have to take the proper minus or plus factors into account depending on how you had to rearrange or commute your operators to achieve that. Now this seems, yeah, okay, nice, you can do that. Why is that good for anything? There is one thing which is very important about this normal ordered products. And this is a very general statement, namely that the expectation value of a normal ordered product with the reference state always vanishes. So whenever you take such a curly bracket object and sandwiches between the reference state, that is, for example, the vacuum state, if you talk about this type of stuff, then the whole thing is automatically zero. And if you think of that in vacuum normal order, then these guys are in vacuum normal order. If you put a vacuum state here to the right, you have an annihilation operator acting on the vacuum. There is nothing to annihilate, so this gives zero immediately. So you see why this, how this comes about. You have these annihilators on the right, which immediately give you zero, and you're done with this. And in principle, in particular, if you look at generalized forms of this normal ordering, this is the defining criterion for an operator chain in normal order. With respect to the reference state you've picked, expectation values are always zero. This is super trivial for the vacuum state, but it's getting interesting if you go to a real state like an A-body Slater determinant as your reference state. Then you can also talk about this normal order, but then things are getting messy because you have these two different families of states, the particle states and the whole states. And now just keep in mind that you want to guarantee this, that the expectation value with this A-body reference determinant of your normal order chain is zero. If you want to do the same mechanism using the annihilation operators, and for the particle states, these are the states which are not occupied in your reference determinant. That's okay, because they're not occupied. You try to annihilate them. Second quantization immediately gives you zero. So that works. These are the annihilation operators in the particle domain. But it's different for the whole states. The whole states are occupied. So therefore, if you want to use an annihilation operator, that wouldn't give zero. It would just give one state less. So in order to make this work, you have to redefine what you mean by creation and annihilation operators. Suddenly you talk about whole creation and whole annihilation operators. And in order to get the same mechanism going for this, you have to interpret the creation operators as whole annihilation operators. Yeah. So you create a particle and that annihilates a whole. Pretty obvious. So the statement with creation operators to the left and annihilation operators to the right, it's getting much more complicated because you redefine now what you mean by creation and annihilation operator. It depends on your reference state. And this whole mess is only done because you want to have this specific property. That's important. That's in principle it. There's not more you need to know about normal ordering. You can always do this normal ordering, this reshuffling, keeping this in mind, using explicit anti-commutation relation. That's tedious, but it's a brute force way to arrive at a normal ordered operator. Not many people do that. Most people use a more elegant way, and this elegant way is Wick theorem. You might have heard about that. I will not discuss it because it's formally not needed to understand the concept. It's a very elegant trick, way, algorithm, if you like, to construct these normal ordered operators and all the prefactors and extras that you get with them, but not necessary to understand the idea. Now let's apply that. Let's go for our Hamiltonian. And the first thing I do is I write down my typical Hamiltonian with kinetic energy, 2 and 3 body forces in standard second quantization in the way we discussed in the first lecture. Then I have intrinsic kinetic energy and two-body interaction. Those terms are two-body operators, so they come with two creation and two annihilation operators, and they are in vacuum normal order, if you like. So the creation operators are on the left, annihilation operators on the right. And then you also have a three-body term. That's the matrix element of the three-body interaction. And this chain of three creation, three annihilation operator. Again, the creation operators are on the left. Everything is fine if you refer to vacuum as your reference state. Now we have seen that I can use other reference states. Oscillator determined which has already A particles occupied. And it might be interesting to convert this Hamiltonian into normal order with respect to such a Oscillator determinant reference state. And I can do that. I can write down how the thing looks like immediately. That's not a big deal. It looks essentially similar. It always has these normal ordering brackets in here because each of these chains is now normal ordered with respect to the reference state. And that's not obvious now because here with my index summation, I sum over all particle states. So the whole states and, sorry, stupid sentence. I sum over the whole states and the particle states. So depending on which of them I capture for my indices here, this might be in normal order to begin with, or I might have to reshuffle because I happen to have a whole state in the game and things are not trivial anymore. So I use these normal ordering brackets here. And I have now three-body matrix elements, which I call W, two-body elements, which I call gamma. I also get one-body matrix elements, although they were not here to begin with. They are called F. And I get a zero-body part, which is just a number, no creation, no annihilation operators attached to it. And this simply comes from the transformation from this vacuum normal order into reference state normal order. And I can, from this transformation, write down what these matrices, these matrix elements are. They are given here. And this is something that you would usually then get from working out all this commutator stuff or from using Wick's theorem. And there's one thing which is interesting and remarkable about that, and which is important for all of the rest. Namely, if you look at this zero-body term, which is just a number, the one-body matrix elements, the two-body matrix elements, they all have pieces of the original three-body force in there. So even the zero-body term knows something about the three-body interaction. And if you now cannot, for technical reasons, deal with this explicit three-body term here, because it's too hard to implement or whatever, and you decide to cut it out, and this is what we call the normal order two-body approximation, then you only lose a bit of the three-body force. You only cut out this W term and these matrix elements. All this stuff is still in your calculation, although you only use technically two-body operators at most. And this goes back to a question that was asked, I think it was yesterday. This is something which might be very clever in connection to the medium to the SRG, to capture these induced multi-body terms. Some of that is here if you use this normal ordering with respect to a non-trivial, non-vacuum reference state. That will be actually the idea of the in-medium SRG. Okie dokie. So that was it with this nasty little formal interlude. But now we are able to understand what these powerful methods like coupled cluster theory actually are. And now it's getting much lighter, so you can relax from now on. Maybe just short break and questions at this point. Okay. Oh, I see a hand. Let's see, can I unmute you?
Yes, can you hear me?
Yes, I can.
Okay, I just didn't really understand in your previous slide how removing this term is different from removing it directly in the vacuum normal order.
Yeah, I mean, if you remove it here, there's not a single matrix element, not a single piece of information on the three-body force left in your calculation. It's simply gone from the beginning. If you remove it here, by this normal ordering procedure, you keep pieces of the three-body terms, those guys, which have been kind of demoted to lower particle ranks. So the three-body force is hidden in the zero-body part, the one-body part, and the two-body part in a very specific way. So in the zero-body part, those matrix elements that show up, they are all for the occupied states in your reference. And this thing is essentially the contribution of the three-body force to the expectation value of the energy in your reference space. So you have a bulk contribution of the three-body force already. In the one-body part, it's the same, but you only have two of the occupied states in the reference state, A and B. And then I and J, they are open. They can be any state. So you have kind of effective one-body matrix elements that you get by summing the other two particles, which appear in your three-body matrix element, over the occupied states in your reference. And it's the same for the two-body term. You have two open indices, it's a two-body interaction, and the third index is summed over all the occupied states in your reference. So in that way, the reference is suddenly very relevant because it provides, so to say, a first approximation to your true physical state for the evaluation of the three-body force. If the reference state would be the exact eigenstate, this would be exact, yeah? So therefore, it's useful, but it puts some kind of emphasis on a clever choice of this reference state. Yeah, I hope that answered your question.
Yes, perfect. Thank you very much.
Okay. Are there more questions? So excellent questions all the way. So please keep going. Okay, so then, after having discussed all that, what is coupled cluster? Coupled cluster is, in principle, a very clever ansatz for the ground state wave function of your A-body system. It's only in the initial formulation about ground states. And that's the first big difference compared to the NCSM type calculations, which always gave us excited states essentially for free. Now it's a completely different story. And that's true for all the medium math methods. Initially, you only target the ground state. And in coupled cluster, you really formulate an explicit ansatz for this ground state, which I call psi CC. And you formulate this ansatz with an exponential of particle hole creation operators. So this T, which is in the argument of this exponential, this is a sum of one particle, one hole, two particle, two hole, up to a particle, a hole excitation operators with unknown amplitudes or coefficients, this little t coefficients here in front. And you package that all into the exponent. Now, this is something which might look like, ooh, that's complicated. Why do we do that? Well, if you don't do that, if you just use this T1, T2 up to TA and apply it to your reference state, which is now really a single Slater determinant, if you do that, then you're back to CI, because this is then just a rewrite of the basis expansion in a particle hole CI scheme. The whole benefit of doing coupled cluster comes from this exponential ansatz. And you see this exponential form popping up in some places. For example, if you do something like RPA, random phase approximation, and you look at the ground state that is generated by RPA, predicted by RPA, and this has this exponential form itself automatically. It has an exponential form with two particle, two hole operators in the exponent. So you see that this exponential is something which might be a very powerful construction. And you can understand why if you, in the back of your head, just do a Taylor expansion of this exponential. then you get a sum over all different powers of this exponent. And this exponent now is a sum of 1 particle 1 hole, 2 particle 2 hole, and so on. So that means the exponential gives you all kinds of product terms of this T1, T2 up to TA. Lots of extra particle hole content, lots of extra correlations. And that's in particularly useful if you start to truncate this sequence of particle hole operators, because this would be exact solution of the full problem. You cannot do that. So the knot where you can truncate in coupled cluster is first of all this particle hole rank of the operators that you put in here. And if you just take the T1, so the 1 particle 1 hole piece, then you call it coupled cluster singles. If you keep T1 and T2, then you call it coupled cluster singles and doubles, or CCSD, which is kind of the standard approximation or truncation level that you look at. If you go further and include the 3 particle 3 hole terms in the exponent, then you call it coupled cluster singles, doubles, triples, so CCSDT. But this in the full form is already too heavy for a nuclear calculation. Nobody has done that for a nucleus in a relevant application yet. But you treat triples, so these 3 particle 3 hole effects, in some approximate way, but this is details that I will not discuss in detail. So the point is exponential ansatz, particle hole operators in the exponent, and you truncate, say, after the 2 particle 2 hole part in this exponent. Now the question is, good, that's an ansatz for my wave function. How do I solve the problem? And the unknowns now are these amplitudes. I don't know them. In order to get there, I plug this ansatz into the Schrödinger equation, H psi equals energy psi. And then after plugging in this ansatz for the psi coupled cluster, I multiply the exponential operator that is on the right-hand side here with the inverse, so e to the minus t, so that this whole equation takes up this form. It's this e to the minus t Hamiltonian e to the t reference state. That's not the coupled cluster state, that's a reference state, the simple Slater determinant, energy, eigenvalue, reference state. And this thing here, unfortunately, is not a unitary transformation, but it is a similarity transformation, which is also good. And you can simply define this as a similarity transformed Hamiltonian, this calligraphic H, and then you are back to this simple looking eigenvalue type equation. It's not unitary, and that has consequences. For unitarity, this e to this inverse, the e to the minus t, would have to be equal to the Hermitian adjoint of e to the t, and that's not the case. But still, having a similarity transformation in there is a very useful thing. The price you pay is that once you truncate this cluster expansion, the resulting approximations will not be variational anymore. So you can beat the Ritz variational principle. You can calculate a ground state energy which is below the exact ground state energy. But that's a minor problem because typically calculations are sufficiently accurate. You're so close to the exact value, it doesn't really matter whether you're a little bit below or a little bit above. And now you have to solve this equation. It looks like an eigenvalue equation, but it isn't, because you already know what this state is. The things you don't know are the energy and the t coefficients, which are hidden in the similarity transformed Hamiltonian. And you have to do something other than solving an eigenvalue problem to determine this t coefficients. And what you do is you take this full equation and multiply from the left with the reference state, with a 1 particle 1 hole excited state, with a 2 particle 2 hole excited state. Then you are faced with a computation of these matrix elements of your similarity transformed Hamiltonian and the reference state and particle hole excitations. And this is a tedious calculation, but you can do that. In order to evaluate the similarity transformed Hamiltonian, you use a Baker-Campbell-Hausdorff expansion to get a handle on these exponentials, but this is technical stuff. You can do that. And just from looking at the original equation, this thing here will give you the energy. The others have zeros on the right-hand side, and these zeros are just this stuff after multiplying from the left with a 1 particle 1 hole or 2 particle 2 hole state, which is orthogonal to the reference state by construction. So therefore, the right-hand side vanishes here. And the only point where the right-hand side gives the contribution, namely the energy, is when you multiply with the reference state from the left. So then you just have reference state scalar product with reference state gives 1 because of normalization. So in the end, this equation gives you the energy, the ground state energy, but you have to know the expansion coefficients, these T's. In order to get those, you need the other two equations. Therefore, these are called the amplitude equations, and this is called the energy equation. This is a coupled set of nonlinear ordinary equations, not differential equations, no eigenvalue problem. It's a set of ordinary algebraic equations for all of these little t amplitudes. And you have to solve this large set of coupled equations to get the t's, and then you plug in here and get the energy. That's how a coupled cluster ground state calculation works. And just to give you a more realistic picture, this looks nice, but if you work these equations out and to the level that you see the little t amplitudes and see the matrix elements of the Hamiltonian, it looks like this. So these are the coupled cluster CCSD equations. This is the equation for the singles excitations. This is for the 2 particle 2 hole excitations, and this is this energy equation. And you don't have to read that. Probably you cannot even read that via Zoom. But the thing that's in there is just these F's and V, which is my gamma from the previous notation. It's not 100% consistent. So the pieces of the normal ordered Hamiltonian and all these T coefficients. So there is a T with 4 indices, so that's 2 particle 2 hole. That's a T with 2 indices, so that's 1 particle 1 hole. And these are the unknowns. And you also have products of T's. That's the power of this exponential ansatz. It gives you these product terms. So that makes these equations nonlinear, and something you have to solve via iterative processes. That's also tricky from the numerical point of view. And it's a completely different computational problem as compared to CI or the no-Koshel model. And this is where you gain something, because this type of problem has a much easier scaling if you go to heavier nuclei. So if you increase particle number, it's much simpler. The computational cost grows much slower as compared to a CI or NCSM calculation. And therefore, it's important that this works completely differently, because this gives access to heavier systems, these different characteristics. Okay, in practice, you never solve these equations, but you go for an angular momentum coupled formulation of the whole thing to make it efficient, to reduce the number of unknowns by using symmetries. But then the equations are even more ugly. And as I mentioned already, this was CCSD. You would like to do triples, at least via some kind of approximation, because triples effect are important. And there are several ways to include triples corrections without going to the full description of the 3 particle 3 hole in the exponent, which is prohibitive. And coupled cluster is the only of these medium math methods which so far have been used with explicit 3-body forces. So you don't have to do this truncation to the normal ordered 2-body approximation that we discussed. You can use a complete 3-body force. We did that. It's expensive, but it's important to kind of validate this approximation that we did with this normal ordered 2-body approximation. Okay, we will look at some results in a minute, but let me just summarize pros and cons of this coupled cluster idea. So a big pro is that it's much more efficient than conventional CI because of the exponential, because you gain additional correlations, products of particle hole excitations that enrich the ground state wave function with more correlations, even if you truncate after two particle, two hole amplitudes. Through these products, you have multi-particle, multi-hole excitations in your state. And this is valuable. It has a mild scaling with A, completely different than a CI approach, and that allows us to go to heavy systems. You can deal with explicit three-body forces if you like. And something that the chemists are very, very fond of, it's size extensive. This is a cryptic statement for a nuclear physicist that never has heard about the slang of the quantum chemists. Size extensivity is just a statement about the scaling of errors in your calculation if you go to more particles. And size extensivity means that the relative error stays constant. It doesn't explode if you go to more particles. And this is something good. I'm not sure how relevant this really is for our nuclear applications. We will diagnose errors explicitly, so we don't rely on this statement alone. But this is a point which is really, really important in the quantum chemistry framework. There are obvious disadvantages. It's not variational. Well, that's a minor detail, I would say. The major limitations are that, number one, the formulation I discussed only gives you the ground state, and it only gives you the ground state energy. So going to excited states or to different observables, you have to do extra work. And since you only start with a reference state, which is a single Slater determinant, that is meaningful only for closed shell nuclei. If you want to go some open shell nucleus, you have to do extra work. And one of the methods that has been used extensively to remedy these two limitations are the so-called equations of motion methods, where you essentially, in very gross terms, put a CI calculation on top of your couple cluster ground state. So you create extra particle hole excitations on top of this couple cluster ground state to describe, for example, excited states. I think somebody in our introductory round mentioned that he's working on a multi-reference version of coupled cluster. This would be a very elegant solution of this limitation, but this is very tough. It's even tough in the chemistry context, and I think it is even tougher in the nuclear context. There are first steps with Bogoliubov coupled cluster, and I think that was your topic. So this is very exciting development, but it makes much of this formalism so much more complicated that it's really, well, tough project. Okay, that's all for the moment about the formal aspects of coupled cluster. Are there questions? Good question by Salvatore. Would it be worth to improve on the bottom using better reference state? Yes, it would. That would be great. But this is exactly the thing where it's getting so much more complicated. Better reference state would mean you go to a, for example, multi-determinant reference state, not just a single Slater determinant, but a superposition of several, or some symmetry broken state, or some symmetry broken and projected state, which is again multi-determinantal. So that would be very useful, but coupled cluster formalism gets much more complicated then. So there is kind of a trade-off whether this is really worthwhile. And for me, the answer is no. I would rather go to a medium SRG because exactly this step is much easier in this other method that I'm going to discuss in a minute. But it would be worthwhile, but it's getting complicated then with a coupled cluster formulation itself. And even in quantum chemistry, they have decades of experience in coupled cluster now, and they are a huge community. There's still lots of discussions about suitable multi-reference extensions of coupled cluster theory. Okay, more questions? Then, since I advertised it, in medium SRG, you remember this slide. It's exactly the same as in yesterday's lecture, this is a one-slide summary of what the similarity renormalization group is in general terms. A unitary transformation of the Hamiltonian written in the form of such a flow equation with a generator eta, which you have to design to achieve the way of decoupling that you would like. This is extremely general. We used it so far in what is called the free space SRG evolution with this kinetic energy generator that I discussed. But we can recycle this whole framework now as an independent many-body method, and that is the in medium SRG. So it's exactly the same idea. I just now reconsider what the Hamiltonian and this generator should be. And I go back to my pictorial introduction. I want to go from my full matrix to some decoupling, and it doesn't even have to be this extreme decoupling. It has to be some partial decoupling which just eliminates off-diagonal matrix elements for a few low-lying states. Then the decoupling yields the eigenstate information, the eigenvalues for these few states, and I don't care about the rest of this matrix. And I want, in the medium SRG context, now to do this step from here to here with a continuous unitary transformation a la SRG. In order to make that even more sound like a many-body statement, we can relate that to our particle hole language from before. And I can specify what kind of decoupling I would really like to have. In the simplest form of the medium SRG, would be ideal if you sort your many-body Hamilton matrix in particle hole channels. 0 particle 0 hole, that's just the reference state expectation value. 1 particle 1 hole, 2 particle 2 hole, and so on. You have this pictorial matrix here. And if I would be able to eliminate these blocks here, then I would have a matrix which has this 0 particle 0 hole block isolated. And this block just has a reference state. So essentially, this means I've diagonalized the problem for the reference state. All of the couplings of the reference state and the other states of my basis are 0. And the reference state becomes the ground state of this transformed Hamiltonian automatically. And if I look at the matrix element that's living in this block, this is the ground state energy. I can simply read it off and done. Now, the only question is, how do I design a unitary transformation that does this job for me? And now it's pretty easy. We have the general framework of the similarity RG, and I use this flow equation to exactly do that. One thing changes. Now the whole evolution of the Hamilton matrix happens at the A-body level. If I want to describe oxygen 16, then this Hamiltonian, which is here in my flow equation, is a Hamiltonian in 16 particle space. And of course, if I think NCSM basis expansion type, I can never ever solve this differential equation because that's 10 to the 10 by 10 to the 10 matrices. But now this normal ordering comes into the game and makes life easier because it gives you an easy handle for a physically motivated truncation again. You write your Hamiltonian in normal order with respect to a reference state, just like couple cluster. You pick a single Slater determinant as a reference state, so the naive shell model state for oxygen 16, for example, and then rephrase your Hamiltonian in normal order with respect to this reference state. And you plug this normal ordered Hamiltonian after truncating away the three-body terms. We discussed that, that's the NO2B approximation, into your flow equation. And you compute or evaluate this whole flow equation at the level of normal ordered operators. So that means everything is technically at the A-body level, but from the computational perspective, you only have to deal with the 0-body, 1-body, and 2-body matrix elements because you've thrown away all the rest. So that might worry you, but remember, some of the multi-particle interactions are absorbed automatically in these lower particle rank matrix elements. So it's not all gone. It's better than the two-body approximation that you would do by cutting away all the three-body pieces without normal order. But this is an extra truncation. And therefore, we call that in medium SRG2 because it's truncated at the two-particle, two-hole level. Now, if you want to do that, you need a generator. And now you can really design many, many fantastic generators. I will not discuss them, just the simplest one to give you an idea. And that goes back to Wegener, he is a condensed matter person in Heidelberg. And he's co-inventor of the SRG, and he used it in condensed matter context. And this idea is super simplistic. I choose eta to be the commutator of the diagonal part and the off-diagonal part of the Hamiltonian. And going back to my little picture, this is the diagonal part and all the rest. And these two blocks are the off-diagonals that I want to suppress. So I simply sort matrix elements, and I assign some matrix elements to this part, the diagonal, some to the off-diagonal, and my generator is the commutator of these two. Very simple, technically very simple. It's intuitive because you can understand why that does the decoupling that you like on the same grounds as for the free space SRG. But unfortunately, everything that's simple is inefficient. So this takes ages in the flow parameter to decouple. So therefore, there are lots of other ideas which have more complicated generators, which are more efficient to reach this decoupling faster. So earlier in your flow evolution, and that saves you computing time, of course. These are the equations, just like the couple cluster equations. I show you the actual equations that you would have to put on a computer. These are now differential equations for the zero-body piece, the one-body matrix elements, and the two-body matrix elements in your normal ordered Hamiltonian. These are also coupled equations, but in contrast to coupled cluster, it's not nonlinear algebraic equations, it's coupled first-order differential equations. Again, completely different numerics behind that. And on the right-hand side, you just recover the pieces that you have, your generator matrix elements, and the pieces of the normal ordered Hamiltonians. So there's quite handy, and it's really easy to handle. Not a big deal at this level. And to see what it does, let's just look at a very simple example. Oxen 16 again. And now I plot here the flow parameter, this parameter that is 0 initially and which runs up throughout my flow evolution. What I plot here is just the value of this zero-body part of the normal ordered Hamiltonian. And this zero-body part is nothing else but the expectation value of the Hamiltonian with my reference state. So this is my proxy for the ground state energy. Once I've reached complete decoupling, that will become the ground state eigenvalue. And you can now track what this expectation value does throughout the SRG evolution. You see it starts slowly. This is a logarithmic scale down here. Therefore, this looks like a kind of smoothed out step function. So you start to evolve with an expectation value, which is kind of around 100, minus 100 MeV. So this is the quality of your single determinant reference state. That's essentially the Hartree-Fock result. And from there, you start with the evolution, with the decoupling, and you see the ground state energy or the zero-body part goes down and stabilizes at some point in the flow. Here, you have reached complete decoupling. No matrix elements connecting this reference state to particle hole excitations anymore. And you can see that in the matrices. Here are the matrix representations corresponding to these gammas and f's and so on. And you see this is my reference state. This is the minus 100 MeV expectation value to begin with. And you see this blue line here and here. These are the couplings of this reference state with all of the excited states in my system. And you see this is my initial Hamiltonian, if I go through the flow, in the end, in this decoupled regime, you see that these blue lines are missing. That's just the first row and first column of matrix elements that have been suppressed to 0. That's decoupling. And therefore, this is my result for the ground state energy. I'm done. You see already here, this method is also only suitable in this simple form for computing the ground state and only for the ground state energy. If you want to have other observables or other states, you have to do more. The big advantage of the in-medium SRG now is that you really have access to these matrices all the time. And it's a unitary transformation. So you just can pick up this matrix, one of these guys, whenever you like during the flow, and decide to do a CI calculation, an NCSM. And this is not possible so easily with coupled cluster because you get non-Hermitian eigenvalue problems. It's super simple with in-medium SRG because you have this information about the flowing matrix all the time. And therefore, we came up with the idea to combine the in-medium SRG with our NCSM, just to use the in-medium SRG to kind of pre-diagonalize our big NCSM matrix. And I don't have to do the full diagonalization with respect to this first entry. I can diagonalize with respect to a block, a tiny reference space, and only suppress this off-diagonal stuff. So that's in some sense a less demanding pre-diagonalization than before. And I'm happy with this because I will use this remaining matrix then in an NCSM calculation. So I can get all the information out of that. And this is in short what this in-medium NCSM is about. I'm running out of time, so therefore I'll skip that and just show you how it works in intuitive terms again with this picture. There are a few technical complications because now you really need a multi-reference formulation of the in-medium SRG. But luckily, this is easy compared to the coupled cluster. You can write down a full multi-reference, multi-determinantal formulation of in-medium SRG and use it, therefore, to decouple subspaces, not individual states. And this is what happens here for carbon-12. It's the same type of figure as before. And again, I show the zero-body part of the Hamiltonian, but this doesn't have the same meaning anymore because now I have this little space which I decouple. And if I look at the matrices, I see what happens. This is my initial matrix. And now you see that the decoupling eliminates this off-diagonal block. This stuff is getting smaller. It's not totally zero here, but it's much smaller than before. And this is what I wanted, because now this block that I have extracted here, that was exactly the Nmax 0 model space of my NCSM. And I've used the in-medium SRG now simply to pre-process my NCSM matrix to further accelerate convergence. In the ideal case, the calculation would be converged at Nmax 0 because this block has been decoupled, and Nmax 0 is easy for each and every nucleus to do. So let's look whether this really works. I added to this plot now the eigenvalues from an NCSM calculation with this matrix for increasing Nmax. And this is initially, that's my essentially old NCSM calculation, and that's done in a Hartree-Fock basis. Therefore, this convergence is so bad with equidistant points here. But this is not the situation I want to discuss. The interesting part is back out here when I've approached this decoupled regime. Then something marvelous happens. All these different Nmax calculations end up on the same spot. So even the Nmax 0 already gives me a converged result. If I go to 2, 3, 4 and my Nmax makes the space big again, doesn't change the energy anymore. So I'm converged by construction. And this is really done by this pre-diagonalization of the in-medium SRG. Of course, there's always a price to pay, no free lunch. As for the free space SRG, you have this approximation with the normal order two-body pieces built into the approach. And that shows up. That shows up by this energy difference here. This line is a NCSM result without in-medium SRG, large space, extrapolated, best you can do. And there is a slight difference between this converged ground state energy here and here. And that's because of this omitted SRG, in medium SRG induced multibody terms, which are not captured by the normal ordering. And you see other things happen. For example, out here, things start to get weird. The energy starts to drop again. There you come in a regime that you've decoupled so much that you boost these omitted higher order terms. You shouldn't go there. That's something which happens specifically for carbon-12, and we fixed it in the meantime by redefinition of the generator, so you can avoid it. But the stuff back here is also an artifact of this normal order two-body approximation. Usually it looks like this. This is a different example for oxygen 20, where you see it just stays flat, and you have a great agreement with the direct NCSM calculation from before. So we can compare now, that's my last point, with the NCSM from before. I can do all the oxygen isotopes, also with this in medium NCSM. These are the green symbols here. And the blue symbols are the straight natural orbital NCSM calculations that we discussed before. And you see the points are all overlapping. There's some scatter, they're moving up and down. Typically, the green points lie a little bit below the blue points, which means there's an additional bit of overbinding that you get from this extra NO2B approximation during the flow. But this is always something like a 1 to 2% effect. So these methods, as a rule of thumb, have a 1 to 2% accuracy for a given Hamiltonian to get you to the exact ground state energy. And it's much more efficient in this medium NCSM context because you can live with tiny, tiny spaces, nmax 0, nmax 2, and you are done. You don't have to go to nmax 10, which really pushes you to the big matrices. So this is a huge relief, and we can look at excited states with this method. So since we use the NCSM in the end, you lift this limitation to ground states. You can do excited states immediately, and you can do nice spectra. And probably this is something I will summarize again in the last lecture, because this is getting a bit too quick. I don't want to brush over this, but this is kind of the key idea of the in medium SRG and the in medium NCSM. And next time I will go through a few of these details again. So that's a lecture on Friday, and I'll discuss the limits of this. So sounds like great, everything is good, but we start to see now a very specific limit in this whole ab initio description, which I would like to discuss, and which is then also the main content for my last lecture on Friday. Okay. Are there any questions left on this?